Hi students, good morning everybody. In today's video, we are going to see about intensity and loudness of sound. Consider a source and two observers. Observer means listeners. The source emits sound waves which carry energy. The sound energy emitted by the source is the same regardless the observer who measures it. That is, sound energy emitted is independent of the observer standing in the region, but the sound received by two observers may be different. Why the sound received by two observers is different is due to the fact that an important fact which is called as sensitivity of ears. The sensitivity of ears of the two observers may not be the same. So in order to quantify such a thing, we have to define two important different quantities which are known as intensity and loudness of sound. First of all, let us see about intensity of a sound. When a sound wave is emitted by the source, the sound wave will get propagated in all directions. That sound wave carries energy. The energy is carried to all possible surrounding points. The average sound energy emitted or transmitted per unit second or unit time is called sound power. Therefore, the intensity of sound is defined as the sound power transmitted per unit area taken normal to the propagation of sound wave. Let us consider this is a sound source. You are considering three areas: area 1, area 2, area 3. Area 1 is at a distance of r from the sound source. Area 2 is at a distance of 2r from the sound source, and area 3 is at a distance of 3r from the sound source. The sound intensity received by the three areas will not be same. It is defined as the sound power transmitted per unit area. The amount of sound power transmitted in one per unit area means across 1 meter square area, which is taken perpendicular to the propagation of the sound wave. So here the intensity I is equal to power by surface area. The surface area is represented as 4 pi r square. So for a particular sound source, for a fixed source, the sound intensity is inversely proportional to the square of the distance from the source. I is equal to power of the source by 4 pi r square. Therefore, from this it is clear that I, the intensity, is proportional to 1 by r square. This is also known as inverse square law of sound intensity. The next one is loudness of sound. Two sounds with the same intensities need not have the same loudness. For example, if you hear the sound during the explosion of balloons inside a silent closed room is very loud when compared to the explosion of the same balloon when it happens in a noisy market. Though the intensity of the sound is same, what you have to understand here is the loudness need not be the same. If the intensity of sound is increased, then the loudness also increases. But in addition to that, not only does intensity affects the loudness, also the internal and subjective experience of how loud a sound is, it depends upon the sensitivity of the listener. Okay, this is also often called as the loudness. Therefore, loudness depends upon both intensity of the sound wave and sensitivity of the air. Yeah, that is, it depends upon the quantity which varies from person to person. But the intensity of sound does not depend upon the observer. Therefore, loudness of sound is defined as the degree of sensation of sound produced in the air or the perception of sound by the listener. So here you must note that loudness is entirely different from intensity. Intensity does not depend upon the person's quality who is observing the sound, but loudness depends upon the person's quality. Okay. Next one, let us see a relation which connects intensity and loudness. Our human ear can detect the sound with intensity level ranging from 10 power minus 2 watt per meter square to 20 watt per meter square. According to Weber-Fechner's law, the loudness is proportional to the logarithm of the actual intensity I measured with an accurate non-human instrument. That is, according to this law, L is proportional to ln I, or L is equal to K into ln I, where K is a constant, and this constant depends upon the unit of measurement. Let us consider two loudness, L0 and L1. The difference between these two loudness, that is L1 minus L0, which is called as relative loudness between two preciously measured intensities, and this is called as sound intensity level. Therefore, mathematically, sound intensity level delta L is equal to L naught 1 minus L naught, which is equal to K ln I1 minus K ln I0, where I1 corresponds to the intensity of L1 and I0 corresponds to the intensity of L0 loudness. So delta K, that is relative loudness, is equal to K ln I1 minus K ln I0, which is equal to K ln I1 by I0. If K is equal to 1 bell, what is bell? Bell is nothing but the unit for intensity named after the scientist Alexander Graham Bell. So, if K is equal to 1 bell, then delta L is equal to ln I1 by I0 bell. But this is practically a bigger unit, so we use a convenient smaller unit which is called as the decibel, which is the practical unit of internal loudness. So 1 decibel is nothing but equal to 1 by 10th of a bell. So what we have to do here is you have to multiply this by 10 and divide this by 10. So when you multiply this equation by 10 and divide this equation by 10, you will get delta L, relative loudness, is equal to 10 into ln I1 by I0 into 1 by 10 bell. 1 by 10 bell is nothing but 1 decibel. 1/10 of a bell is called as a decibel. So delta L is equal to 10 ln I1 by I0 decibel with K is equal to 10. So for practical purposes, we use logarithm to base 10 instead of natural logarithm. So delta L, that is relative loudness, is equal to 10 log I1 by I0 to the base 10 decibel. Let us now discuss the topic vibrations of air column. Musical instruments like flute, clarinet, nadaswaram are known as wind instruments. These wind instruments work on the principle of vibrations of air column. The simplest form of wind instrument is called as an organ pipe. What do you mean by an organ pipe? It is a pipe which is made of either a wooden or a metal pipe which produces musical sound. For example, flute, clarinet and nadaswaram are organ pipe instruments. Organ pipe instruments can be classified as two types. One is closed organ pipe and another one is a open organ pipe. In this section we are going to see about closed organ pipe and open organ pipe. Clarinet is the best example for closed organ pipe. What do you mean by a closed organ pipe? A closed organ pipe is nothing but a pipe with one end closed and other end open. If a sound wave enters through one end, it will go and strike at the closed end. After striking at the closed end, it gets reflected. So the reflected waves and the incident waves, sound waves inside the closed organ pipe overlap with each other, and they will have a phase difference of 180 degree with each other. So inside the air column, inside the closed organ pipe, certain vibrations, or I can say stationary waves, are produced inside the vibrating air column. In this closed organ pipe, we are going to see what are the different forms, different modes of vibration and the relation between them. This is a closed organ pipe such that the one end is closed and another end is open. Inside this closed organ pipe there will be an air column. If you make the air column inside the tube to vibrate, stationary waves are produced inside the closed organ pipe, and in such a way that nodes are formed at the closed end and antinodes are formed at the open end. Let us first consider the simplest mode of vibration of air column, which is called as the fundamental mode. So when the air column inside the closed organ pipe vibrates in the fundamental mode, what happens means a node is formed at the closed end and an antinode is formed at the open end. Let L be the length of the tube and lambda be the wavelength. So for fundamental mode of vibration, we can write L is equal to lambda 1 by 4, where lambda is the wavelength. And here one node and one antinode is formed, and the distance between a node and an antinode is lambda by 4. So here we can write L is equal to lambda 1 by 4 in the fundamental mode of vibration in a closed organ pipe. So lambda 1 is equal to 4L. The frequency of the note emitted is F1 is equal to V by lambda 1. So instead of lambda 1, substitute 4L. So F1 is equal to V by 4L, which is called as the fundamental note. The frequencies higher than the fundamental frequency can also be produced by blowing air strongly at the open end of this pipe. Such frequencies are called as overtones. This diagram shows the mode of vibration of a closed organ pipe, the second mode of vibration. In the second mode of vibration, what you have to understand is here two nodes are formed and two antinodes are formed. So in the second mode of vibration, there are two nodes and two antinodes, and here this is an anode and this is an antinode. So the distance is lambda by 4. Here from this antinode to node, the distance is lambda by 4. From this node to this antinode, the distance is lambda by 4. So there are 3 lambda by 4s coming into play. So I can write L is equal to 3 lambda by 4, lambda 2 by 4, or 4L is equal to 3 lambda 2, or L is equal to 3 lambda 2 by 4, or lambda 2 is equal to 4L by 3. So for this case, the frequency is F2 is equal to V by lambda 2, which is equal to, if you substitute lambda 2 is equal to 4L by 3, we will get F2 is equal to 3V by 4L. But V by 4L is nothing but equal to F1. So F2 is equal to 3F1, and this is called as the first overtone. Here the frequency is 3 times the fundamental frequency, and so this is called as the third harmonic. Let us see the next possible mode of vibration in a closed organ pipe. In this mode of vibration, 3 nodes and 3 antinodes are produced. So here I can write L is equal to 5 lambda 3 by 4, or lambda lambda 3 is equal to 4L by 5. The frequency corresponding to this is F3 is equal to V by lambda 3. Substitute lambda 3 is equal to 4L by 5. We will get F3 is equal to 5V by 4L. But you know that V by 4L is nothing but F1. So F3 is equal to 5F1. This is called as the second overtone. Or this is called as the fifth harmonic, because the frequency is 5 times the fundamental frequency. Hence it is clear that in a closed organ pipe it only odd harmonics are present, and the frequency of the nth harmonic F1 is equal to 2n plus 1 F1. Therefore frequencies or harmonics are in the ratio F1 is to F2 is to F3 is equal to 1 is to 3 is to 5 is to 7. So it is clear that in a closed organ pipe only odd harmonics are present. Let us now once see about the vibrations of air column in an open organ pipe. A flute is an example for an open organ pipe. What do you mean by an open organ pipe? The organ pipe which is open at both ends is called as an open organ pipe. In an open organ pipe, musical sound is produced by the vibrations of the air column inside the pipe under different modes. Let us see the different possible modes of vibration in an open organ pipe. Let us consider the open organ pipe of length L. In the simplest mode of vibration, the air column called as the fundamental mode. And here in the fundamental mode of vibration, two antinodes, one antinode at one end and another antinode at another end is formed, having one node at the center at the midpoint. So let us take L to be the length. L is equal to lambda 1 by 2, or lambda 1 is equal to 2L. The frequency of the first note emitted is F1 is equal to V by lambda 1. Lambda 1 is equal to 2L. So F1 is equal to V by 2L, which is called as the fundamental note. The frequency is higher than the fundamental frequency can also be produced by blowing air strongly at one end of the open organ pipe. Such frequencies are called as overtones. In the second mode of vibration in an open organ pipe, we have two nodes and three antinodes. Since it has two nodes and three antinodes, we can write L is equal to lambda 2, or lambda 2 is equal to L. Therefore, the frequency F2 is equal to V by lambda 2, or V by L. 2 into V by 2, V by 2L, or which is equal to F1, which is called as the first overtone. Here N is equal to 2, that is called, therefore it is called as the second harmonic. In the next possible mode of vibration, it will have 3 nodes and 4 antinodes as shown in the diagram. This diagram shows the third mode of vibration having 3 nodes, 1, 2, 3 and 1, 2, 3, 4 antinodes. Therefore, here we can write L is equal to 3 by 2 lambda 3, or lambda 3 is equal to 2L by 3. Therefore, F3 is equal to V by lambda 3, which is equal to 3V by 2L, which is equal to 3F1, which is called as the second overtone. Here F3 is equal to 3F1, so which is called as the third harmonic. So in an open organ pipe are all harmonics, and the frequency of the nth harmonic is Fn is equal to Nf1. Therefore frequencies of the harmonics are in the ratio F1 is to F2 is to F3 is to F4 is equal to 1 is to 2 is to 3 is to 4. So here you must understand that in an open organ pipe all harmonics are produced. The ratio of their frequencies of all harmonics is given as F1 is to F2 is to F3 is equal to 1 is to 2 is to 3. But in a closed organ pipe, only odd harmonics are present. The ratio of the frequencies in a closed organ pipe is given as F1 is to F2 is to F3 is equal to 1 is to 3 is to 5.